Hello, the video you're about to watch is a recording from a presentation given to a country which was interested in implementing OpenCRVS and wanted to find out all about the architecture of the system. Hope you enjoy it.
My name is Euan Miller. I'm the Chief Technical Officer of OpenCRVS, and today I'm going to be talking to you about the technical architecture. Let me just introduce the agenda. So what I'll be talking about is, first of all, what are the general technical requirements of a digital civil registration system? So what should you expect from that sort of thing? And then how does OpenCRVS respond to those requirements in terms of its configurability, its scalability and data sovereignty, the total cost of ownership, how it interoperates and is standards compliant, its security and its performance. And then we'll end the session with a Q&A. So I'll be discussing, first of all, what are the technical requirements of a civil registration system? Well, first of all, it must be configurable because it's going to be used in a variety of different countries. It has to be scalable because it needs to cover countries with all sorts of population sizes, up to 200 million people plus, and that would apply to any kind of medium-sized large country of 50 million plus. It has to be scalable to cover your entire population. It must protect data sovereignty. That means that it must be entirely hosted in the country in order to comply with your legislation. We don't want any data to be stored in the cloud or internationally. So it's got to be deployable in country, in an in-country tier 2 or 3 data center. It has to have a low total cost of ownership. So the customization, configuration, and maintenance of this software must be really, really easy and obviously not cost you so much. It's got to be interoperable with healthcare, national ID systems, social protection systems. It's got to be secure because by nature, it's going to be storing a lot of personally identifiable information of citizens, and therefore it needs the highest levels of protection from cyber attack and compliance with any data protection regulations in your country or region. It's got to work offline in low connectivity areas, in rural areas. It's got to be performant. It's got to be, really quick and seamless user experience, despite some of the heavy processing that's required running functions such as record search and deduplication. So your civil registration system really has to address all of these requirements. So I'm going to spend the bulk of the presentation now talking about these requirements and how OpenCRVS responds to them. So first of all, let's talk about configuration, whether things are scalable, and sovereignty. So when we were making the architecture choice about how to build OpenCRVS 5 or 6 years ago now, we were looking at, well, what are the choices available to us and how do they comply with configurability, scalability, and data sovereignty? Well, traditionally, before the millennium, most applications were monolithic. They were the data layer, the presentation layer, application layer. Everything was combined into one application, referred to as a monolith, which you would install directly on the operating system, on the virtual machine. And that seems very simple, and it's very appropriate for small startup type applications. And it was the only choice available based on the technologies at the time. Now, post-millennium, there became a new term called a service-orientated architecture. And this was really trying to make the monolith more scalable by breaking up these services into individual applications and deploying them on individual virtual machines or servers. And then around about 2015, a new conversation started to happen. And that was because thanks to the introduction of a new technology. And the new technology was called Docker containerization. And that allowed you to have a service-oriented architecture running, where each service was running inside a Docker container, which could be replicated and scaled. It took that concept of having a business service in SOA and making it even more granular and more easy to substitute. So very small granular business services could be independently scaled. At the same time, thanks to technology in Amazon and Azure and Google, places like this, they took the microservice concept, and instead of having services, they would have business functions that could be scaled. And the Docker containers, you didn't even have to worry about them. It would be the cloud provider that would distribute those containers across internationally if possible. So those are the sorts of 4 architecture choices we had to choose from. So we had to decide which one of these is configurable, scalable, and sovereign. Well, if we think about the monolith, as I was saying, all the data, all the layers of the application are combined into a single application. And you scale that by scaling the operating system or virtual machine. So that's quite an expensive use of CPU and other resources. And every single configuration you make of a monolith is essentially an entirely new application. So that isn't really very scalable. It's certainly expensive to scale, and it's not very configurable. So that wasn't going to work for Ernie's. So a service-oriented architecture, we have decoupled groups of business services. Each one can be scaled by operating system and virtual machine, just like a monolith. So again, it's getting quite expensive to scale. Architecturally, it's getting closer to what we need for configurability. But a service-oriented architecture usually also depends on centralized data storage and often an enterprise service bus. So these are getting expensive limitations of whether you can scale. You really have to vertically scale the data storage. You can't horizontally scale it. So again, this is quite expensive. So microservices. So these are independently scalable and configurable services, each with their own database, powered by Docker containerization, therefore extremely cheap to scale. We can scale it horizontally, and we can do that on our servers without needing cloud. So therefore, this seems to satisfy configurability, scalability, and sovereignty. Great. Well, what about serverless? So as I was saying before, this is like microservices, but it's at an even more granular scale because we're talking about functions, scaling functions on demand, thanks to the availability of cloud resources, which can cross-board in AWS, Azure, etc. So unless you are lucky enough to have an AWS data center in your country and you have a contractual agreement to that cloud is going to stay in country, then that doesn't help us with our data sovereignty problem. So unfortunately, that's not something we can do right now, maybe in the future. So we only really have one architecture choice in order to make a configurable, scalable, and sovereign civil registration system, and that's a microservice architecture. So there's a lot of content on the internet about microservices. I'm not going to talk about that in any great detail that you can research if you want to in your own time. But at a very high level, what microservice architecture is that each of your services is restricted to a single business function. So on the right-hand side here, you can see here's an example microservice architecture for a very simple shopping application. You have each service is independently deployable and scalable in a Docker container, and each service has control over its own databases. So you can see we have an account service where orders may be placed, and an accounts database. We have an inventory service where stock may be stored for this shop, an inventory database, and a logistics shipping service and a shipping database where those deliveries may be controlled from. And each of these microservices interoperates via API. And there's an entry point, which is an API gateway to the client. So that's a microservice architecture. And one of the really key things about this, which is powered by the actual underlying server architecture, is imagine you want to change something. Imagine you want to change something in your application. If we're talking about a monolith, then that application is installed directly on the guest operating system. So if you wanted to change the shipping service, the logistics service, there's no way to do it unless you take the whole application offline, change it, and bring it back online. So that leads to downtime. And the great thing about microservices and Docker is that each of these microservices runs on top of the Docker engine, on top of the host operating system, a single OS, and you can take down one of these services without taking down the entire application. You can change it, bring it back online. And if you have a load balance cluster, you can do that with no downtime at all. So this is really a microservice architecture at a high level and how it works. So OpenCRVS, as you can imagine, there are lots of business services with a civil registration system. And this is a list of all of the microservices that OpenCRVS gives you in OpenCRVS core. And on the right-hand side, you can see we use a lot of different database technologies in the stack. So it looks quite complex. Actually, for a microservice application, this is actually not a lot of microservices. Some microservice applications literally have tens, hundreds of microservices. So we've tried to minimize them as much as possible into business functions. For example, we have, I won't go through all of them, but just at a high level, we have a login application, a client application. We have an authentication microservice, which deals with OAuth 2 and creating multi-factor authentication codes when you're logging in. We have an API gateway. We have a user management service, which handles your users and their authorization privileges. So maybe you can conceptualize that, you could potentially configure or customize OpenCRVS so that the auth and user management microservices were replaced by single sign-on that you use in country, for example. We have a workflow microservice, and that's used for managing the state of a registration. If you think about that registration being and having an initial declaration, a validation step, a certification step, registration step, issuance step. So this microservice handles that registration business status. We have a search microservice, which is powered by a database and engine called Elasticsearch, which is really fast for deduplication and audit trail. We have a documents microservice. So imagine you're uploading supporting documentation, attachments to your application, photographs of passports, ID documents, forms to accompany your birth or death application, and that would be stored in a very specific database, blob storage, which is Amazon S3 compatible. So with microservices, we really can choose the right technology for the right business function, and this is a list of OpenCRVS services. One of them, config. This is a service which distributes the country configuration to all other services. So Rather than configuring each service individually, we have a service which is dedicated to distributing a configuration across all the other services. And that brings us to the final service I want to talk about, which is the country config service. This is the service which you use when you want to configure the infrastructure that OpenCRVS is installed on, application settings, your form configuration, your content, your languages that you support, the certificates that you configure, and any APIs. So that's the, I'll talk more about that in the next section when I talk about cost of ownership. So I won't talk about this in much detail at all, but there's a diagram of how these services are deployed, which ones are externally available, which ones are inside the Docker network, and where the country config sits in this architecture. And this is available on a documentation website, and you can look at this again at your leisure. So, okay, we've got a architecture decision, but there are challenges to having a microservice architecture. It's obviously much more complex than a monolithic application. With the benefits of configurability and scalability come challenges. First of all, it's a challenge conceptually if you are new to the concept, and there can be a steep learning curve regarding that, regarding microservices and Docker containerization. Modular, granular configuration of various tools can take time to learn, and they can be very challenging to network and monitor, deploy, and update. So we needed to address this. We needed to address this total cost of ownership of this architecture choice. And in the next section, I'll be showing you how we've responded to these challenges to lower the cost of ownership and make life as easy as possible for you. So, first of all, you don't really have to care about any of these microservices. They are all bundled together into a monorepo on GitHub. So you don't have to, when you're deploying, configuring OpenCRVS, download individual microservices from individual GitHub repositories. So there's basically two approaches to having repositories for microservices. You can either have a one microservice per repository or a monorepo, and we chose monorepo because this makes life a lot easier for maintainers. So all of these microservices on the left go into one repo, and you don't really need to touch it. If you think there is something that OpenCRVS does not do, if you think there's a feature, which there generally always is something that you would like that we don't do, then you can open an issue on this GitHub repository and request that feature. And we will build it with you during the pilot implementation phases. And therefore, you will get a supported release every time with the extra things you need. And we really welcome country contributions because those are the things which sustain us as a project. So we certainly hope that you will do this, but you don't have to. It's not something you have to do during implementation configuration. You can simply request a feature, subscribe to it, and it will be delivered to you when it's ready. So there's only one microservice that you need to configure, and that is the country configuration repository. So we take that one at the bottom, the country config, and we put it in a new repository, and you can fork this and do whatever you like here. And what can you configure? Well, you can configure the entire infrastructure, the entire delivery pipeline if you want. You can configure the certificates. So that is done via an SVG file. And it's very easy to design that and to put into the SVG code handlebars where you want the dynamic data to appear in your certificate. You configure your form configurations here. And this is the only coding required, which is done in TypeScript. And that allows you to control every question you ask in your form. You can configure the administrative structure here. So that is the jurisdictions in your country, the borders between states and districts, provinces, etc. You can configure all of your language content here, all the text that's displayed in multiple languages using international standards for internationalization. You can control all your application settings, and that's done very easily with CSV files and JSON or via APIs. And you can configure how OpenCRVS notifies staff and beneficiaries via SMS or email or other method. You can customize identifiers at the point of birth and death. You can customize business intelligence, analytics. These are all done via APIs. So it's one microservice to configure. So that lowers the TCO quite a lot. Secondly, the challenge we were talking about where microservices are difficult to deploy, well, we have taken care of that for you. So we supply automated installation of dependencies like firewalls, VPNs, and automated deployment scripts via GitHub Actions. So you may be used or have heard of continuous deployment. You might have heard of tools like Travis, Azure Pipelines, Circle CI. All of these are automated tools to automatically provision your servers at the click of a button. Automated task to test that your system is backed up and to restore a backup onto another server in order to test it. That's all done at the click of a button. So really, really, we've taken away all of that effort of deployment from you. We have adopted a very low TCO approach to code. The entire stack, up front end and back end, is written in one language, that is TypeScript, which is a strictly typed syntax for JavaScript and Node.js, developed by Microsoft. So this makes it really easy to distribute development tasks across a team. You don't need different developers with different skill sets. They just need to know one language, and you can share effort in any part of the application at any time. We have additionally adopted a low coding approach when it comes to the mobile experience. And we've made use of progressive web application, PWA technology. And this offers a native-like app experience with one code base for both mobile and browser. So there's no need to maintain a separate native application code in a different language. No need for you to distribute, install, or update Android APK files with all your staff. It's all done in the browser and installable like a desktop or mobile application using PWA. So that drastically lowers TCO as well. Monitoring. So the challenge of monitoring, how do you monitor all these services and make sure that they're running? Well, we supply the Elastic Logstash and Kibana stack inside OpenCRVS for application monitoring. So you can view live logs from all the services and get notified when, if any of them were going down, or if any resource required scaling. If you run out of disk space, you will get notified long in advance that you may need to increase the size of your disks. So this is built in and given to you by default. All these alerts are set up by default. So what are, and in other sort of subjects regarding total cost of ownership, let's talk about what sort of servers do you need. Well, here is a server diagram. You can look at this in more detail. We have a requirement for a virtual private network. You will have your staff who access the application by VPN, and implementation technical staff who do the same thing. And there is a production network of servers, and this network depends on your national scale. At a minimum, I'll talk about the minimum requirements in one moment, but we have a QA, quality assurance server, where you can test your changes, and a backup server where all the data is backed up on a daily basis. And that backup can be deployed to a production mirror. So you can have a duplicate production environment so that you know your backups are restoring properly without exposing PII to any technical staff if you want. So at a minimum, you need 4 servers. Depending on your country size, if you have a population in the region of, say, 50 to 100 million people, then you can have a load balance cluster of an additional 2 nodes, so 6 servers. And if you are installing OpenCRVS in a very large country of, say, 150 plus million people, 150 million people plus, then 6 nodes are required. So you can load balance across those servers. Other technical requirements, you will need a second level wildcard subdomain for your DNS and SSL certificate generation. And OpenCRVS can provide that for you, and it can provide the VPN for you also. There are some accompanying tools and services which you will need. And these are very low cost, really small cost, approximately $1,500 a year. You will need a GitHub organization to store your private country config code and customize your continuous delivery GitHub actions or pipelines. You will need a container repository like Docker Hub to host the compiled Docker container. That's just where we can pull that from. So these are 2 repositories for code and Docker image. You will need Slack messaging. This is so that you can easily communicate with the core team at any time. And we can also pipe all of the monitoring alerts directly to Slack. So it's very easy for you to immediately determine the health of your application. You will need a Sentry. This is a tool which can catch application bugs and send you a report if anything happens and your users are complaining about something. Sentry will catch the bug and send it to Slack. You will need a paper trail account or something else where you can store system logs externally. Obviously you want to maybe do some forensic analysis in the future, and having a server where you can save logs helps in a nice UI. It's not essential, it's an option. Another option is pingdom account. This is so an external system can ping each microservice from an external location in case something happened to your data center. Anything can happen in any data center. Obviously, there can be fires or things like this, or so you can find out immediately if your data center is okay. And finally, you should get a password manager, and this is something you can use to securely store the National System Administration passwords and secrets. So these are all very, very cheap services which only make your installation more robust. Finally, you will need an SMTP service. So that's something that you can use to send emails, or you could send SMS. It's up to you. This is in order to deliver login 2-factor authentication codes and communicate with staff and beneficiaries. Obviously, optional SMS is available if you want it for beneficiaries who are on GSM phones. And of course, costs for these can scale depending on your size. So that is additional tools and services that you will need to bundle into your total cost of ownership of this DPG. So clearly, steps have been taken to lower the total cost of ownership of an OpenCRVS as a microservice architecture. But what is the cost of ownership when you're integrating with existing or new systems? How does OpenCRVS interoperate? OpenCRVS exists within an ecosystem of eGov services, such as social protection systems, and perhaps even legacy or existing civil registration systems in other countries, I don't know. But so just to give you an idea of what steps we've taken in terms of civil registration and social protection standards. Well, OpenCRVS is a core contributor and compliantly interoperates with the Digital Convergence Initiative, CRVS, and Social Protection Standards Organization. So you can see the types of people who are involved in the organizations who are involved in this on the left. And we have contributed to the standards of what a civil registration person should be, what a place should be, the names, and many other data points. And this seamlessly allows you to take use of the interoperability needs for certain workflows, such as ceasing allowance upon death, enrolling people into child allowance, all of the social protection systems which depend on civil registration. So we're standards compliant. And we interoperate across digital public infrastructure by being a core contributor and compliantly interoperating with the Center for Digital Public Infrastructure, G2P Connect, government-to-person payment programs. So we are compliant with these APIs, and these APIs use DCI standard payloads. So very much at the heart of efforts to interoperate across e-government. Since conception, we have been standards compliant with healthcare. Our data model is FHIR standardized. So that's a HL7 healthcare standard. So that enables real-time integration with healthcare facilities directly at the common locations where births and deaths occur at the moment of event. So your hospitals, your clinics, where births and deaths happen, medical staff can submit notifications directly into the civil registration system. So FHIR enables us to have a really standardized database model, which is fully documented. So it's very easy to learn about how our databases are organized. And it uses standardized ISO codes that support medical and civil registration needs, such as ICD-10, cause of death codes, things like this. We have bundled in the stack the FHIR standardized interoperability middleware called OpenHIM. This interoperability layer is a key component of the OpenHIE, that's the Health Information Exchange Organization. It's a standardized architecture layer in that framework. And so it's really plug and play with any healthcare system. What about national ID? Well, we use OpenID standards when we authenticate national ID numbers that are being supplied to us in our forms with systems like eSignet, which you might be familiar with. It's the MOSIP team has created this, allowing you to validate that the national ID is being supplied is authentic, and the citizen themselves can give OpenCRVS permission to receive from the national ID system data points. So that protects data sovereignty, the the data sovereignty of citizens, as well as being standards compliant. We are already integrated fully into MOSIP, and on registration of a birth event in OpenCRVS, MOSIP is automatically informed. A unique identity is created for life, so that at the point of death, it can be invalidated. So we also are standards compliant with a number of other features which can really help. For example, we use the humanitarian data exchange standards in order to initially configure jurisdictional and administrative boundaries for your country. So all of your states and districts, with all the statistical unique IDs you already use in country, these seamlessly work with OpenCRVS at the point of installation, and you can update them. So there are other interoperability use cases as well. For example, the event notification I talked about, where an application can be submitted from a hospital. We have an API, so that could be submitted from any other system, such as a social protection system, or maybe a public portal. So if you want the public to notify their own births and deaths, that's a possibility. We can integrate with any other national ID system via our webhook architecture. And we have a record search API that allows any government system, approved system, to search our records. Fourth interoperability use case, at the point of registration, just before the registration happens. So you can imagine the staff have validated all the forms, they validated the supporting documentation, they click register, we deduplicate, and then we're happy to actually register in the back end. At that point, you can allow any legacy system to asynchronously generate other identifiers that you may need, or perform an integration into a legacy system. If you're implementing OpenCRVS in parallel with an existing system and you're gradually scaling, that could be useful. And finally, you can update that administrative structure, the locations in your country at any time. You can add statistical information such as population sizes, crude birth rates, add more offices, change the administrative structure. All of this is possible via an API. So, in summary, we've clearly taken steps to ensure that OpenCRVS interoperates in a standardized and flexible way with other systems. But how secure are these entry points? And how secure is OpenCRVS in general? So, we mentioned security. Well, interoperable clients use OAuth 2 standards in order to authenticate. And these can be set up by the National System Administrator through the UI. So they will get OAuth 2 secrets and passwords, which can be used to authenticate a client, receive a token, and within 10 minutes you can make requests, and every request you make is audited, and they are rate limited. So the API clients are standardized in terms of security. OpenCRVS is encrypted and authentication and authorization strictly controlled. So personal data is algorithmically encrypted at rest in the databases and protected during transmission via SSL and VPN. When authenticating with OpenCRVS as a user, multi-factor, two-factor authentication is enforced on each login. So you will get a 6-digit code, which can be sent to you via email or SMS, potentially via an authenticator app if you so wish. And that really is a very secure way to access the application. As I said, user types and authorization permissions are managed, and these are managed by the National System Admin through the team user interface. And users can be deactivated. They can have their permissions changed, and immediately you can segregate the user interface and personally identifiable data to only the users who need it at any given time. Therefore, you can control onboarding and offboarding of staff in a secure way. OpenCRVS is, like any other digital system in the world, is constantly under threat from cybersecurity, from hackers, the ever-evolving ways in which hackers will try to access the system. And because it stores personally identifiable information, it's a target. So we must and regularly make sure that OpenCRVS is independently penetration tested to government level cybersecurity standards. So we have reports which are done on a regular basis on each release, and we get very, very good feedback. So for example, here is a quote from one of our independent security testers telling us that already from the results of the first assessment, it was evident that the OpenCRVS application had a good security posture. The security fundamentals were sound. So we take great care to ensure that OpenCRVS is up to date with the threats that are out there on a regular basis. And of course, keeping OpenCRVS up to date is critically important. So, do all these configurability, scalability, interoperability, and security capabilities come at a performance cost? How does OpenCRVS perform at scale, offline, and in areas of low connectivity? And how is this quality maintained? So let's talk a bit about performance and quality assurance. So the OpenCRVS progressive web application, user, registration download, and registration submission experience is designed for mobile first, offline, and low connectivity working environments. So we have outboxes where applications are sent into a holding pattern until connectivity is available, and then they will sync. You can work entirely offline, and when you have connectivity, sync, download new registrations for validation, or submit ones. So that's been a priority for us, this mobile first, offline, low connectivity first user experience. And it's regularly performance tested. So here is an example of one of our performance tests that we run on each release. Each test submits thousands of requests concurrently, and each of these requests is a registration submission. It's a search and a real-time deduplication check. So that registration is compared against every other registration in the database in the millions and checked if there's a duplicate. And the 95% average request rate on a load balance cluster for a country of scale was 2.8 requests per second, with up to 12 concurrent requests and no failures reported. And so this scale equals registration rates for a country with a population of 200 million people. So how do we maintain the quality? Well, we release relatively often. Obviously, we're a small team. We'd like to always release more often, but we do 2 or 3 major or minor releases per year. And in between, we do many ad hoc hot fix releases throughout this calendar. So you can expect regularly to receive new features and functionality. And it's very important that you kind of get familiar with the kind of release support that's available. This is a diagram of our Git repository branching pattern. We have a master branch, which is always aligned to our latest release. And we branch from that when we're introducing bug fixes or hot fixes, and these go through quality assurance, a quality gate. And those hot fixes will be available for 6 months from the previous release. In the meantime, we're always making new things based on your requests, your issues that you've opened. So whenever we're working on a new thing, that will go through a quality gate to ensure that all the automated tests, we have not broken any functionality with this new feature. This release will then be beta tested for approximately 1 to 2 months, and then will be stably released and available to the public. So we take quality assurance very, very seriously with these quality gates. Many of them on the left here are automated in GitHub Actions. So we have automated unit tests, automated compilation tests, automated deployment tests to our environments to make sure the deployment process works. And we have manual user acceptance testing, quality assurance testing done on every feature and every hotfix. And when we're doing a beta release, we'll do a sanity test and then go through a full regression test before the stable release is available. And we'll have a third-party security penetration test also. So you can be sure that our release is up to date and secure as possible. And then as I said, keeping OpenCRVS up to date is really important. So we want to make that very easy for you. So we provide very detailed migration notes in our documentation on each release, and we provide automated database migration scripts. So that will happen automatically. You don't need to run database migration scripts manually. It's all taken care of, and you can monitor how their process in our stack, in our Elastic Kibana stack. So that really brings me to the end of this presentation.